Hello, welcome to a brand new video on the Yas channel. Today we're going to be going over motors, the hardware and software. Well, this series is going to be split into multiple parts. Today we're going to be going through the more hardware side of motors, what you should know about them, when you should use motors, different types of motors, the different types of motors, and everything you should know. And your design team, your mechanical team should know about motors. So the programming side and the hardware side is both on the same page. Let's get started. First things first, you should know is the two types of motors. There is brushed and brushless. I'm going to have to say that you're going to most commonly see more brushless nowadays, as was a first year in FRC, I had no idea what a brushed motor was. I had a judge ask me the difference between brushed versus brushless. I had no idea, but now you do, as brush motors have a DC power input. They have no integrated relative encoder, so they have nothing in here that can read like an angle measurement, like what angle it's outputting at, or how many rotations that it's just spins. They're also really heavy, so there's a lot of downsides, I would say, to it compared to a brushless motor, which is why we see it more common nowadays. They have a three-phase power input or integrated controller, so that means that they have uh, a motor controller as well as power that will supply into it to allow these motors to run. They also have a integrated relative encoder. So you would see these motors, they wouldn't have a absolute encoder, but some teams use it for their arms or whatever, and they can still get an accurate angle reading from this. And that is because they may have a hard stop or whatever. But either way, they have some kind of method to read the spins, any sensor units that are on this motor. They're also lighter and more energy efficient compared to brushed motors. There are now also two types of motor controllers. There are external and integrated. You might I My team uses a lot of external encoders or external motor controllers, as uh, integrated are more expensive. They have that 3 power phase or DC power, so they're compatible with your brush motors if you had one. They require a sensor cable. Um, so it would be, I'm pretty sure it is this green wire here is the sensor. Correct me if I'm wrong. But they do require another wire compared to a integrated one, and they take up a lot more space, as when you're planning your robot, you have to make sure that you leave room for not just the any motors you have, right? You have your wheels here, but you also have to make sure you designate a spot in your robot for each one of these motor controllers, as every motor that you had would need some kind of spark max or spark flex, and they do take up space. Integrated is, however, it takes up a lot less space, as it is built inside of the motor, and you can it handles some sensor stuff, and it attaches to the motor. They are more expensive to replace. Now, this is going to be a lot of text, but there are some extra notes here. One is going to be the term thermal mass. Thermal mass is going to just be how much heat can your motor withstand, right? We have a motor here, and it is trying to spin um, against something that it's trying to like spin into something, but it's kind of stalling it, right? It's not letting that motor spin, and that can cause it to heat up. And how much heat that motor can withstand is called thermal thermal mass. And certain motors can handle this extra heat a lot better than other motors. For example, a Neo 550 really sucks at it compared to some other motors like Neo Vortex Krakens, or Kraken's X60s or 44s, right? This you might hear. It's referencing to a previous game called Reefscape. In 2025, we had a big old ball, and a lot of teams, what they would do is they would have like a motor here and a motor here, and then they would suck in the ball like this, and this caused a lot of stalling to happen because these motors, right? They're being really pushed to their limits to compress this ball that does not want to be compressed. However, some teams are did it more successfully than others. Teams that did do it, they did see a lot of current and voltage being used to pick up this one game piece because it takes up a lot of current, or it takes a lot of work to get this motor to move because it doesn't want to move. It's being like pressed against some other things or super pinching it. And so this can cause this one mechanism taking a lot more amps and a lot more voltage than you want it to, because you have to run your drivetrain, your arms, your elevators. You really don't want this one thing to take up all 12 volts of your robot. Or if you are going to do this, proceed with caution. Um, Other you have a lot higher risk of burning out, or causing a overloading your Rio, or just like not things not working the way you want it to be. Got some other notes here. Something you should also know is going to be backlash. Backlash is going to be that tiny gap that between two parts, which that are supposed to be tightly mesh. For example, gears. Right? You have your gears. Oh, this is gonna. Oh, that turned. Okay, pretend this is a nice gear, and then you had another gear right here. Oh, yeah, that's a gear. Right. Okay. Pretend those are very beautiful gears. And you notice this little crevice between there. That is that can cause a lot of problems, as when you change direction, the mechanism has to take up that gap before it can actually moves, and this can feel like a delay or wiggleness, slop, or looseness. This is normal. However, this could cause a lot of problems if it's on a larger scale, because the arm or elevator wobbles a bit when it stops. There's a delay when trying to move these two mechanisms, and then there's also going to be difficulty tuning it, as the mechanism never behaves going the same way forwards or backwards because of this gap. Backlash. Backlash will make your life harder if it hasn't already. When a mechanism slops, you have a much worse time tuning it. Yeah. And here's some things that your build team and design team should keep in mind. Um, Pistons shift pinions. Pinions? Okay. Um, Pinch shift pinions. Okay. For 20 dp gears, there's some vendors. They sell pinions that may say 8T, 10T center distance, which means that the tooth profile is altered to allow for the smaller pistons, which are allow for smaller pistons than pinions than what is usually possible. This can be useful, but never try to use these on an arm because they have a lot more backlash compared to normal pinions. It's okay for a elevator because there's gravity always pushing back against this backlash. Our arm, you don't always have that gravity supporting you, and then they wear out a lot faster and make more noise. Something you should also know is going to be about your gear ratios. High gear ratios for max planetary stages, like 5 to 1, 6 to 1, 9 to 1s, they have a lot more backlash compared to lower ratios, for example, 3 to 1s, 4 to 1s. So you want to try to avoid these as possible. Make sure you have a reduction after using one of these stages, as it reduces the effect of the backlash For example, if you're using a 9 to 1, right, you want to transition that downwards on the scale. You don't want to go from like a 6 to 1 to a 9 to 1. You rather, if you were to use when you use a 9 to 1, then go down to like a 3 to 1 or something like that. However, typically you try to want to avoid these, but if you had to, you want to make sure it goes down the gearbox ladder. Planetaries will always have more backlash than a well-made custom gearbox. Motors and motor controllers. Not every motor controller you find in FRC or find will be allowed for FRC. There are some that are regulated, and you should check to see if you're allowed to use them, and as these could be changed every year. With You can find these with recalc. Recalc, you can also find a bunch of other helpful things like your gear ratios, your feedback feed forward values, or whatever. I think it's your feedback. And then this, even though this tutorial is a bit more general use, we still have a YAMS mention, one of our mechanism libraries. And YAMS only allows brushless motors and motor controllers. So sorry teams for using, if they're using brush motors. YAMS is currently only supporting brushless, and I'm pretty sure we'll stay only using brushless motors, as that's what teams use more commonly nowadays. Then last thing I want to talk about in this video is going to be some status lights. On your motor controllers, or any mechanical electrical thing on your robot, there are lights, and they actually do mean something. I recommend go looking at them, as this image isn't the greatest, but you can find this on just searching up status light references in FRC. And yeah, I hope you enjoyed today's video. In the next video, we're going to be talking about a bit of the software of how to program a motor. Especially, this is going deep dive into how to program a motor using YAMS, one of our mechanism libraries. So if you enjoyed this video, please hit the subscribe button, like the video, and have a good day.